Alright, so we're going to talk a little bit about number theory. And this is going to be an extremely brief introduction. We don't have a lot of time to get into a lot of the really deep material, but we can give an overview and some of the really interesting things that you can think about when you think about numbers. So we're going to be studying numbers, but I should tell you what I mean by number. So number theory really doesn't study any types of numbers. It doesn't study fractions really or irrational numbers like pi, for instance. We really are studying what's called the counting numbers. And now the counting numbers, some people have slightly different definitions, but for us, we're going to say that the counting numbers are the positive integers starting at 1. So we have 1, 2, 3, 4, 5, all the way up. And we can just keep going, right? There's no largest counting number. So we can also say that these are the positive integers. And just kind of for convenience, I'll probably just say number. And for this entire lecture, number will just mean a counting number. 1, 2, 3, 4, 5, on up. So usually, now what do I mean by usually? More in our common language, we think about counting numbers as adjectives. So just like, you can describe the color of your car by red. Red is an adjective. You can talk about the number 2 as an adjective. There are 2 cars. Okay, so it can describe the number of something. So just some examples. 2 cars. 3 apples. 7 students, etc. So all of these counting numbers I'm using here, 2, 3, and 7, I'm using them as adjectives. And that's kind of how it goes. We don't really think about, what is the number 2? What is the number 3? What is the number 7? What's special about those numbers? But that's what number theory does, is it actually sort of turns metaphysical and looks at actually the structure of these numbers that we use to describe cardinalities of sets. So number theory, if you kind of want a definition, studies, one way to say it is the inherent properties of the counting numbers themselves. And of course I'll probably do this again. The pound sign or hashtag, if you prefer, will just mean number. Okay, so it's pretty interesting if you think about, you use these numbers so frequently as adjectives, but now all of a sudden we kind of want to turn inward and look at what are the properties of these numbers that they have inherently, or that they have just by, 3 is 3, but what is it about 3 that makes it 3? What's the difference between, say, 3 and 4? Is there really any difference other than, of course, 4 is larger? But just in the structure of the number itself, what are the differences? Okay, so let's look at some examples of what I'm talking about. Okay, so let's just start with the first counting number, 1. Now, of course, 1 is a very special number, but in terms of representing it visually or anything like that, having 1 of something, there's not a lot of pattern recognition we can use. Okay, so we want to try to recognize patterns in the ways that we can organize, say, one object or two objects or three objects. So that's kind of the idea. So if I have one dot, there it is. There's not really much I can do with it. Now let's look at two. If I have two dots, there's also really not much I can do with two dots. I'm thinking about looking at dominoes or dice and the way that the dots are arranged. So of course, as we get to larger numbers, there'll be more interesting ways to arrange dots. Okay, so two, there's really not much I can say. I just put them next to each other. So what about three? Well, I can put three dots right next to each other, but I can also do something else that's kind of cool. I can make a triangle with the three dots. So that's kind of interesting. Two, I can just put them right next to each other. Of course, I could sort of reorient. In three, I could put them right next to each other. But, a triangle is kind of a nice shape. And we'll see that again with four. Okay, so with four, I can put the four dots right next to each other, or with four, again, we can do something kind of cool. We can make a square, a 2x2 square with our four dots. So somehow 3 and 4 have some sort of property or a way to arrange 3 or 4 things that's different than having 1 or 2 things. Okay, so hopefully what I'm doing is becoming clear in that you can just think about different ways you can arrange different sized sets of objects. Now 5, and you'll notice we can always just put the dots right next to each other. So we have 5 dots right next to each other. With 5, there are other things we can do. Okay, we could make sort of like the start of the triangle. We could make sort of like a pentagon shape with 5. And you can keep going and digging, there's really no end to the ways you can arrange things, but let's just leave the 5 dots by themselves. There's not an obvious one. Okay, so triangle and square, that seems interesting enough. 5, feel free to try to think about the ways you can arrange 5 dots, and you can come up with some cool patterns, but for now, let's just leave 5 as 5. I really want to look at 6. 6 is where things start really getting interesting, because we can have our 6 dots side by side, or I can make a 2x3 rectangle like that. That's a nice way to organize. Or I can also do something similar to 3. I can actually make a triangle with my 6 dots. So with 6, I actually have 3 pretty interesting ways to arrange my dots. And then we can just go on and on and on. So maybe we can look at another example. 12 is kind of an interesting one. So we can put 12 dots side by side. We can put 6 and then another row of 6 like that. Or we can make 3 rows of 4 like that. Okay, and I'm just trying to pick the most natural ways to organize the dots. You can just keep going forever, and in fact, a lot of what number theory does can sort of be boiled down to representations of the counting numbers by other counting numbers. So, 12, I can represent 12 as 2 rows of 6, 3 rows of 4, 1 rows of 12. Even things like sums of squares, how many ways are there to represent a number by a sum of two squares or a sum of three squares, etc. I mean, all of these pretty deep theorems really boil down to how can you arrange, uh, some number of dots. And in that sense, number theory is very beautiful because the ideas are so simply explained. Now, the solutions to some of the problems involve all other types of math, even calculus and complicated algebra. But the questions we can pose about the counting numbers are very simple and easy to understand. So it's very interesting to talk about and get people interested in why you might want to do higher levels of math. Okay, so this is going to go through some of the essential definitions of kind of our introduction to number theory. And some of these should be familiar, but we just want to nail them down. And the big dichotomy is between divisor and multiple. And they're really easy to mix up, and that's okay. But let's just think about it. So again, I just want to reiterate that when I say number, I mean a counting number. So a number D is a divisor or factor. I'll prefer to use divisor, but it might be more common to use factor. Either way, it's the same thing. So a divisor of n if there is another number such that n is d times m. And in this case, we say that n is a multiple of d. Just a couple of ways you can think about this, going back to our definition of multiplication, if d is a divisor of n, then that means we can take a group of n objects and partition them into d equal groups. And then geometrically, we can draw a d by m rectangle, kind of like we were doing before. So to nail down these definitions, let's look at some examples. So 3 is a divisor of 12. Or in other words, 12 is a multiple of 3. Okay, so you kind of see this dichotomy. 3 is a divisor of 12, so the divisor is the smaller number. And then 12 is a multiple of 3, right? That's kind of the idea. I can take 3, 6, 9, 12. If I just go by my multiples of 3, I eventually hit 12. And then visually, we have either, whichever way you want to think about it. You can form equal groups. So you can form 3 equal groups like this. Here, here, and it's here. So again, this is kind of showing this divisor D. So I can form 3 equal groups of 12 objects. Or, kind of how I had it, you can form a 3 by 4 rectangle. And that number m is just going to be whatever the quotient is when I divide n by d. And there will always be no remainder when d is a divisor of n. Maybe that's a little bit more technical way to say it. You can always, if you recall with division, you can always divide d into n. You can write n is equal to q times d plus a remainder. And here, the remainder will always be 0 when d is a divisor of n. So that's a little bit mathy, but again, that's another valid way to define what a divisor is. Okay, so make sure you kind of have in your mind the distinction between a divisor and a multiple. Okay, so let's just go through some quick facts about divisors. So first of all, every number, every counting number, has 1 in itself as a divisor. Okay, so there's sort of a really tricky point about the number 1, right? Because 1 is 1, right? So 1 only has one divisor. I mean, it has 1 in itself as a divisor, but because 1 is itself, there's only 1. Okay, so every number other than 1 has at least 2 divisors. All right, so we're going to kind of leave 1 on the back burner for a minute. And now, if n has exactly 2 divisors, then n is called prime. Okay, so 1 is not prime because 1 only has 1 divisor. But, for instance, we have 2 is prime, 3 is prime, 4 is not prime because it has 3 divisors, 5 is prime, 7 is prime, 11, 13, 17, 19, 23, etc. Okay, so you can just keep listing out the primes. There are actually infinitely many primes. So, another way to think about these numbers, you can't form a rectangle other than just a 1 by n rectangle, just listing out all the dots next to themselves. Now, if n has more than 2 divisors, like 4 has 3 divisors and 6 has 4 divisors, then n is composite. Okay, and here's this point about 1 that can be really tricky. This is a great question to ask students once you kind of introduce what a prime number is and what a composite number is, kind of have them debate, is 1 prime or composite? And it's sort of just the way we've defined it, that 1 is neither prime nor composite. Now you could give other definitions where maybe you could say, oh, well, maybe 1 is prime, but we actually want to exclude that. And that is purely historical and conventional. It sort of makes things fit together a little bit nicely, but really, 1 is just 1. Okay, you can call it whatever you want. But what we're really able to do is distinguish between numbers greater than 1 into 2 categories. A number greater than 1 is either prime or composite. Okay, and geometrically, composite numbers, typically we can arrange them in cool ways, like we've seen in terms of rectangles, whereas primes, there's not as much we can do with primes. Okay. So one really interesting concept, now that we have the idea of a divisor down, is the greatest common divisor, or the greatest common factor, I'll just say. I'll use greatest common divisor, abbreviated GCD, of 2 numbers. Okay, so let's take, for example, 6 and 15. Now, to find the greatest common divisor of 6 and 15, all I want to do is just list out all of the divisors of these 2 numbers and then take the largest. So what are the divisors of 6? Well, we know 1 is a divisor of 6. And then 2 is a divisor of 6 because 2 times 3 is 6. 3 is a divisor of 6 because 3 times 2 is 6. And then, of course, the number itself is always a divisor. So 1, 2, 3, and 6 are the divisors of 6. For 15, let me write them down, and I'll sort of leave it up to you to verify that these are indeed the divisors of 15. Okay, so we look at the list of divisors and look, what's the largest number appearing in both lists? Well, that number is 3. So then we say that the GCD of 6 and 15 is 3. Okay, pretty easy. So we can just list out the divisors and pick the largest one. That's the greatest common divisor. So there's a really cool way to visualize the greatest common divisor. And in an activity, we'll actually see a really interesting application of the greatest common divisor. But let's say we draw a rectangle. And how big is this rectangle going to be? Well, it's going to be a 6 by 15 rectangle. Okay? So let me try to partition this. We'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, that wasn't terrible. And now 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6. Okay, so this is a 6 by 15 rectangle. So how can we visualize the GCD, the greatest common divisor? Well, the greatest common divisor is going to be the number for which we can take a square of that dimension. So if the greatest common divisor is 2, a 2 by 2 square. If the greatest common divisor is 5, a 5 by 5 square. And tile or cover this rectangle with squares of that size. So since the GCD is 3, that means that the largest square I can use to cover this rectangle is a 3 by 3 square. So what I can do is, here's a 3 by 3 square. I'm just going to cover this rectangle with 3 by 3 squares. And now any common divisor of 6 and 15, I will be able to cover this rectangle with squares of that size. But the greatest common divisor is going to be the largest rectangle. Okay, so notice I could have covered this rectangle with 1 by 1 squares, but that's not the greatest, right? The greatest is 3. So these 3 by 3 squares I can use to cover up this rectangle. Notice I couldn't use 5 by 5 squares, because if I did a 5 by 5 square, I'd be left with just one row down here, and I couldn't cover that without overlapping. Okay, so that's kind of a way you can visualize the greatest common divisor. We'll do an activity where we actually see how the greatest common divisor is related to gears turning and interlocking, and it's kind of a really cool application in that sense. Okay, so let's move on. We'll talk about one more thing and then we'll be done. Okay, so finally let's look at the least common multiple, or LCM. And now I think that least common multiple is the most standard way to say this. I don't know of another. So how do we find the least common multiple of two numbers? So again, let's use our example of 6 and 15. Now instead of listing out the divisors like we did with the GCD, we're going to list out the multiples. So what are the multiples of 6? Well, we have 6 times 1, which is 6. 6 times 2 is 12. 6 times 3 is 18. 6 times 4 is 24. 6 times 5 is 30. Then 36. Okay, and we can keep going. And now, unlike with the divisor list, the multiples list is actually never going to end, unfortunately. So we're just going to write out a bunch. All right, let's do the same thing for 15. So 15, that's 1 times 15. Then we have 30, 2 times 15, 45, 60, 75, etc. Alrighty. So the least common multiple, as the name suggests, is the least multiple, the smallest multiple in each list that appears in both lists. So that's going to be 30. So notice we just start with 6, 12, 18, 24, 30, 15, 30. That's the smallest number that appears in the multiples of both 6 and 15. That's the least common multiple. Okay, so we can write the least common multiple of 6 and 15 is 30. Okay, so there's a really amazing um, fact and connection between the least common multiple and the GCD, and that's the following formula. So if I take a number n and I multiply it by another number m, that's going to be the same thing as multiplying the GCD of both of the numbers times the least common multiple of both of those numbers. Okay, and this is a fact that there are lots of different ways to see why this is true, but it's one of those very beautiful facts that has a lot of very nice good visualizations for it. So let's just see this example in action. So let's take 6 times 15. Okay, so I'll let n be 6 and m be 15. Now, that's supposed to be the same thing, multiplying 6 by 15, is multiplying the GCD of 6 and 15, which recall is 3, times the least common multiple of 6 and 15, which is 30. And we can indeed verify that 6 times 15 is 90, and 3 times 30 is 90. So our formula works out. And there we go. There we have it. There's a lot more I want to say. Like I said, we'll do a little bit more explanation with GCD and least common multiple in an activity. But that's an extremely brief, maybe it didn't feel brief, but that is an extremely brief introduction to number theory. And with these ideas that we've introduced, we can really go a long way and ask even some of the most difficult and challenging questions that still have not been answered in number theory. So I hope you enjoyed it, and let me know if you have any questions, and that's it.